Welcome back to the Explainer. All right, today's the day we build maybe the most important part of our 8-bit computer. We're building its brain.
So think about where we are. We've got our memory, our registers, the ALU, all the individual sections of our digital orchestra are basically tuned up and ready to go. But right now, it's just silence. Nothing's happening. They're all just sitting there, waiting for a signal, waiting for someone to tell them what to play and when to play it. See, we're missing the conductor.
And that conductor, that's the control unit. It is the absolute heart of this whole operation. This is the one component that orchestrates every single action inside the CPU. It's the part that generates those super precise signals that tell all the other components exactly what to do from one clock tick to the next.
Okay, so how does this thing actually work? Well, here's the plan. We're going to introduce our digital conductor. Then we'll get into the simple, but really powerful, idea that makes it all tick, the state machine. After that, we'll look at the CPU's heartbeat. And then we'll break down the first two crucial steps in that rhythm, the fetch and the decode.
So, you might be wondering, how does one little unit manage all this insane complexity? It's not magic, I promise. The secret is this beautifully simple, really elegant concept called a finite state machine. You'll often see it called an FSM.
And an FSM is, well, it's pretty much what it sounds like. It's a machine that has a finite, a limited number of states it can be in. So at any given moment, it can only be in one of these specific conditions. And it moves, or transitions, from one state to the next based on a really strict set of rules and whatever input it's getting at that moment.
You know the perfect example of this? A vending machine. Seriously, it starts in an idle state, right? Just waiting. You put a coin in, and boom, it transitions to a has money state. You push a button, it moves to selection made. Then it gives you your snack, and then it goes right back to that idle state, ready for the next person. It's just a simple, totally predictable sequence. Our CPU's control unit, it works in the exact same way, just, millions of times faster.
Okay, so let's take that vending machine idea and apply it to our CPU. A CPU doesn't just do things randomly, right? It operates on this constant, rhythmic pulse. It's like a heartbeat that drives every single thing it does.
And that pulse, that's the legendary Fetch-Decode-Execute cycle. I mean, this is it. This is the fundamental operation of pretty much every computer ever made. It's simple, really. First, it fetches the next instruction from memory. Second, it decodes that instruction to figure out what on earth it's supposed to do. And third, it executes that command. And then it just repeats over and over and over again, billions of times a second.
So our finite state machine, that vending machine brain, that's the engine driving this whole cycle. Every single step in its sequence lines up perfectly with one tick of our system clock. And we have a name for these steps. We call them T-states. So for every single clock pulse, our FSM clicks over to the next T-state, and that's what moves the CPU forward through the Fetch-Decode-Execute cycle. All right, let's get into the weeds and see how this actually works. We're going to focus on that first absolutely crucial phase, the fetch. I mean, before the CPU can do anything at all, it needs its marching orders, right? It has to go get the next instruction from memory. Okay, so it all kicks off at T-state 0, which you can see here as S_fetch_0. On that very first clock tick, the FSM asserts, which is just a fancy way of saying it turns on, two really important control signals. First, it tells the program counter, the PC, to put its address out onto the bus, and at the exact same time, it activates MAR load. That tells the memory address register, the MAR, to snatch that address off the bus. And just like that, the command is on its way.
Now this next part is where things get really clever. In the very next state, T1, the RAM is off doing its thing, trying to find the data at the address we just gave it. But while that's happening, the control unit doesn't just sit around and wait. No way! It sends out a PC_inc signal, which tells the program counter to go ahead and increment. Think about that. It's already getting ready for the next instruction cycle before this one is even done. This kind of multitasking is exactly why modern CPUs are so ridiculously fast. Every single nanosecond is put to work.
Okay, moving on. By T-state 2, the RAM has found our instruction and it's ready to go. So the control unit activates the bus, selects the RAM, and lets that instruction data flow out. At that precise moment, it also asserts IR_load, which commands the instruction register, the IR, to latch onto that data. Bam! The instruction is caught. The fetch phase is complete.
So let's just pause and think about what we just did. In just 3 tiny clock ticks, 3 T-states, we have successfully grabbed one instruction from our program in memory and pulled it right into the CPU's instruction register. It's fetched, it's secure, and now it's ready for phase 2.
Okay, so the instruction is sitting safely inside the instruction register. What's next? Well, our little FSM moves on to the next phase, decode. It's got the raw data, the ones and zeros, but now it has to figure out, what does this actually mean? And this little piece of code here really shows you what the FSM's next job is. The machine is in its decode state, and it's looking at a specific part of the instruction called the opcode. You can think of the opcode as the verb in a sentence. It's the action word. It says what to do. So based on that opcode, the FSM makes a choice. Is this a load or store kind of thing, or is this a data manipulation thing, like adding 2 numbers? This simple if-then logic is exactly how the FSM figures out which path to take, which sequence of future T-states it needs to actually carry out the command. And there you have it. We've fetched the instruction from memory, and we've decoded its meaning. Our digital conductor, the control unit, has officially read the sheet music. It knows exactly which part to play next. And this process, it's the same universal first 2 steps for any computer, whether it's our little 8-bit machine or a massive supercomputer.
So the instruction is now firmly in the control unit's hands. The big question is, what happens next? Well, that all depends on the opcode. How does the CPU actually add numbers, or store data in memory, or make a decision to jump to a totally different part of the program? Well, that's a story for our next explainer.